Hello everybody, you're very welcome to part 2 of software testing. So in part 2 we're going to look at testing tools. So what are testing tools? Well, there's a range of tools that help you in testing. There's tools that help you in terms of requirements testing, in terms of static analysis, in terms of design, in terms of data preparation, test running tools, comparison tools, test harnesses, performance, test tools, dynamic analysis tools, debugging tools, test management tools, and coverage measurement tools. So let's look at each one of them one at a time. So what are requirement testing tools? Well, they check that what the user has expressed their desire to get is what they're going to be getting. So they can check, if I create diagrams in UML or things like that, they can check that they're consistent with each other, or at least that the use cases match the interaction sequence diagrams or the class diagrams and things like that. So there are tools for checking the design, and even in terms of naming of things, that things are named consistently, and that we can pump out overlays between the different diagramming techniques. Static analysis tools are all about looking at the quality of the software, so it's examining the code but not executing it. Things like cyclomatic complexity, that is to say, if I look at a loop in my code, are there way too many loops in my code? So if I count the number of whiles and fors in the code, how many is there? If I look for recursion, is there a lot of recursion happening in the code? If I look at even parameter passing, so I'm not running the code, I'm just using a program that will parse the code and look for the keywords that it knows for a while, if, things like that, and it's just checking if there's an awful lot of loops and branching. The system will tell you, dude, that's going to be slow because there's an awful lot of looping going on here. Or even the length of the loops, if there's a lot of code inside a loop. And some tools are smart enough to say, look, some of this code doesn't need to be in the loop at all. It can be initialized outside because it isn't changing inside the loop at all. So if it knows something like that, it'll let you know about that, which is cool. A test design tool is really looking at the code, and it can generate diagrams from it. It can look at, if I say that the system needs to achieve the following criteria, it can look at the code and say, well, this code doesn't appear to be achieving those criteria. But in a very specific and formal way, you have to express the goals of the code, almost predicate logic kind of ways. In terms of test data preparation tools, so there's so many really useful tools that allow you to look at the data, generate data that is like live data but isn't live data, pseudo live data it's sometimes called, data that will allow you to test the system without actually having to get real user live data. Because if you have real user live data, then you have information, names and addresses of people, and that there'll be confidentiality agreements and non-disclosure agreements that need to be signed. Whereas if I just generate fake data that's like the real data, that's much handier. So we can get test data preparation tools that create data or get some data from the internet, and it'll allow you to edit it, all kinds of cool stuff like that. We've got test running tools, and we've 2 pages of those. They are tools that tell the tester rather, what's going on, so they can run tests as though it's being run by a human tester. Often how this works is, I run the first test myself, and I have a record button, and I record, almost like screencasting, exactly what I do in the first test. And then I capture that macro, that program that's recorded exactly what I do. And then I tell the computer, rerun that test again, but change the inputs or change the outputs or change whatever. And then I can generate hundreds and hundreds of scripts or little tests that are slight variations on the original test I did by hand. So it's so much faster than being done by a human tester. And of course then, if I have those test scripts for one test, then I can use variations of that for other testing. The key thing here is, when I run a test, I should know what output I expect already, and then I can compare it. So let's say my computer program, the goal of the program is to multiply the number by 2. If I type in the number 4, I'm expecting an output of 8. So if I tell my testing code, input the number 4 and give me an error message if the output is not 8, Input the number 0 and give me an error message if the output is not 0. Input the number 1 and give me an error message if the number is not 2. Input the number -1 and give me an error message if the number is not -2. So that you specify both what the inputs are and what the expected outputs are. You can run hundreds of little programs and then see which ones have failed. And interestingly enough, sometimes when you find an error in the code, you send it back to the developer, they fix that error. When they give you back the code, you need to test it an awful lot more again. Because sometimes when they fix one little bug, they cause a load of other bugs to happen. So that's called regression testing, where we test the fixes that have occurred. Because very often fixing one thing will cause weird side effects elsewhere. Other test running tools include character-based input that fakes as if it's a user typing in information. So again, if I type in a few samples, the testing tool can generate then hundreds of variations on those samples. And we have tools that simulate graphical user interface as well, so it can capture me using the mouse or clicking on buttons or keyboard inputs and rerun that and rerun variations on it as well. There are comparison tools, and they are key. It's comparing the actual results with the expected results. So as I said, if I'm a program multiplying a number by 2, let me put in as many variations as possible. Let me put in the letter A and make sure the output is, the letter A is not a number if I'm doubling it. So things like that, make sure we test for a range of outputs and tell the system what expected outputs we're supposed to be getting, or tell the comparison tool, and it'll tell you in what cases it failed. And then there are test harnesses, which I mentioned already. If we want to pluck a module, a single module out of a program, we can stick it in a software test harness, which then allows us to test that individual module one at a time. Often as well, when developers develop code, they leave the user interface till the end. So they've all the code working, they've got the bubble sort code working, but they don't have it printing out to the screen. So if you plonk the developer code into a test harness, it'll fake up an input and output user interface for you, which is great. There's also software simulators. So let's say if I'm writing code for Android and I don't have an Android phone, I can use an Android simulator to develop the code to get it working on an Android phone. And then when I get an Android phone, I can show that that app works. Also, if I'm, again, writing code for a nuclear power plant, it's as well to get a simulator for a nuclear power plant rather than use the real thing. Because if I'm testing the code that says vent the power rods now, I don't want to test that on a real nuclear power plant, so I want to test it on a simulator. There are performance testing tools that just looks at if we stress test the system. So if we put a lot of requests into the system, if we have 100 users logged on, how well does the system perform? If we have 10 users logged on, how well does the system perform? If we have 1,000 users logged on, how well does the system perform? And then how long does the user have to wait for feedback from the system if there's 50 more people logged on than the previous test? And again, we'll get lots of reports for performance testing tools with graphs, time series graphs that'll show how the response time goes up a lot as the number of users increase. Often there's a turning point whereby if I have 50 users in the system will work fine, but after 51, the response time goes to hell. And very often when customers buy software, they specify I need a response time of 2 seconds or less. Then you say, well, if you want a response time of 2 seconds or less, no more than 50 users can log on to the system. Let's look at dynamic analysis tools. So they provide runtime information on the software while it's running, looking at what kind of disk space it's allocating, looking at what kinds of devices it's using, what kind of server blades it's accessing, what kind of processor power it's using up, what kind of memory it's taking up. And it might point out that there are pointers being used or arrays that are empty that are not being used or linked lists that don't link to anything. So if it identifies things that are there but aren't being used, the dynamic analysis tools can point it out. Debugging tools are probably the ones we're most familiar with if there is a problem with the code. Normally when we run our code and it gives an error message, we normally put in a print statement, or we can run a debugging tool which says, maybe we say, run this program one step at a time and show me the value of each variable as each step of the program goes along, as each line goes along. And then when it gets to the point where the error occurs, we can see what value all the variables had at that point. So that's really effective. Debugging tools are great. And test management tools are almost like project management tools. They're tools to manage the testing process itself, not the code. So they keep records of the number of tests we've ran, how many tests we need to get done today when the testing has to be over. It records all the log results, records any problems we've had with the testing process overall. It says who tested what when, essentially, on what operating system, using what code. So that's a project management tool. And coverage measurement tools are just to make sure every possible bit of the code is tested. So let's say I have an if then else, and my condition is if x is less than 5, then do this, else do this. So I need to make sure when I'm testing that the value of x is both greater than 5 and another test occurs where the value of x is less than 5. Because if I don't test where a value is less than 5, then I might never go into the else part of the code in my testing. But if the else part of my code isn't right, then I might never find out in testing that the else bit doesn't work. But then the first time the user goes into the else part of the code, it crashes. So coverage means, do I execute every line of code? And think about with an if statement, if there's code in the else and code in the then, and then code in the else, I need to make sure I've run the code in the then and the else in my tests for every if statement. And there could be 1,000 different if statements in the code. So I need to make sure for every one of those if statements, the then and else part of each statement is executed. And maybe I need to check if the else part in the first if statement is executed, how does that impact it if the then part of the second if statement is executed? Or how does it impact if the else part of the first if statement is executed? How does that impact if the else of the second part is executed? So I need to make sure we cover as much of the code as possible. Just as a general approach to testing, I would say, if I didn't have a test plan at all and I just sat down and thought of tests myself, I'll try this, I'll try that, what about if I did this, what about if I added a date of birth less than today's date? And then I identified what issues are going on and thought up of specific inputs. We'd call that unscripted or manual testing. We like the idea, or we'll prefer the idea of scripted, where we have already identified what things we might test. So let's have a look at what a script looks like. Run the program and see if it works. Just if I double click on the icon, does it run? If it has to open a list, does it do it? Does it allow me to add items in? Does it allow me to move an item? Does it allow me to delete an item? Does it allow me to change stuff? So if I have a test plan sorted already, that's very effective. What I would say is, though, it's good to be loose and open to adding to that test script when I'm testing. So if I think of another test that I should add on during the testing process, don't be tied down by the test plan. Add in extra stuff if you need to. So although I would never advocate not having a test plan or a vague plan, I wouldn't advocate sticking strictly to a test plan either. Have the test plan, follow that, do all the tests in it definitely, but have the freedom then to add in new tests. If you think of something as you're going along, definitely add that in. So a detailed plan is great, but don't be tied to it. And definitely, the more you automate, the more difficult things get. It's good, some tests are good to automate and some aren't. It's good to have the freedom to manual test things as well. If I automate everything and then I leave the company and somebody else takes over my job, if they just run my scripts and don't know what they're doing, they might be missing things that they shouldn't do. So automate for the current situation, but don't rely on those same testing scripts for testing other software, is what I'd say. Maintain control, though, and keep Keep removing any tests that you think are no good or redundant or have been superseded or just worn out. Like, you've used this test on the last 3 different software projects. It's probably time to get rid of it and consider more adding new tests in. There is, of course, a cost-benefit analysis. The more time I spend testing, the more costs. So with these new tests I'm adding on, am I finding faults? Invest in time in terms of committing resources. And if I'm the tester, champion the idea of automate where relevant and don't automate where not. And champion definitely automation. Talk to everybody, talk to the developers, talk to the analysts, even talk to the customers if possible, and script where possible. The kinds of tests I think you should automate are the ones that are run many times, particularly if we find an error and then we fix it, and then we check the fixed code. That's regression testing, or stuff that's boring to test. Stuff that would be, automate stuff that would be expensive to perform manually, either in terms of time or in terms of operating systems or things like that, and automate tests that are difficult. But don't automate tests that are rarely run. Don't automate tests that aren't very important. Don't automate tests about usability. So the user experience or the user interface, don't try and automate them. Don't try and get one of those goofy programs that says it will analyze your screen and tell you whether it's a good user interface or not. The way to test if a user interface is good is to get users to use it. There is no other way. I don't care what anybody says about automated testing tools that will test the user's screen for you, the user interface. A manual test must be done by users to use the system. That is the only way you find out if a system is usable. There's no other way. So that's testing tools. Thanks very much. We'll see you on the next episode.